Hi everyone, this is Alice Gao. In this video, I'm going to talk about two important concepts. The first one is the bias and variance trade-off, and the second one is cross-validation. At the end of the previous video, I talked about the overall goal of machine learning, which is that we want to find a hypothesis that generalizes well. In other words, we want to find a hypothesis that can predict unseen examples correctly. Achieving this goal is difficult, and one reason is that there is a trade-off we have to struggle with all the time. The trade-off is between complex hypotheses that usually fit the training data very well versus simpler hypotheses that may generalize better. So how do we find the sweet spot in between, find the hypothesis with the right complexity? To do this, we need to consider the bias and variance trade-off. Let's look at what is this trade-off. This picture illustrates the bias and variance trade-off very nicely. So on the x-axis, we have the model complexity, and on the y-axis, we have how much error we're making when we're trying to predict the data set that we have. So this graph is trying to show you how does the error change as the model becomes more and more complex. You can see that the error first decreases, right? And then it reaches a minimum somewhere in the middle, and then it increases. So there are 2 points where the error is the highest. One point is when the model is really simple, and another point is when the model is really complex. We want to find the spot in the middle where the error is minimized. Now, how the error changes can be explained by how the bias and variance of our hypothesis changes. So as our model becomes more complex, the variance of the model increases and the bias of our model decreases. So now let me tell you about what is bias and what is variance. When we think about the bias of a hypothesis, we think about this question. If I have infinite data, how well can I fit the data with my learned hypothesis? Notice here, data is not the issue. We have as much data as we want. So what is limiting us is the particular form of hypothesis. So bias is about what is the effect of our model, of our hypothesis on how well we can fit the data. A hypothesis with high bias usually looks as follows. It's usually very simple, and a simple hypothesis usually has very few degrees of freedom, right? There's not a lot of choices for parameters. A simple hypothesis usually makes very strong assumptions, right? Think about it. If you have a simple function, the function says, oh, data have to follow this particular form. There's no freedom in terms of how it might look like. So because we have such a simple function, then it tends to not fit the training data very well because we just don't have enough freedom to be able to accommodate all the possible different points in the data set. Now here's the problem with a hypothesis with high bias. If we can't even capture the training data very well using our hypothesis, then how can we possibly hope to predict unseen data well using our hypothesis? Because we're assuming that the training data and the unseen data have some relationship with each other, right? So you can see that if a hypothesis has high bias, the model itself, the hypothesis itself is limiting our ability to fit the data well. Now let me talk about variance. If we're thinking about the variance of a hypothesis, we want to answer this question. how much does the learned hypothesis vary given different training data? So when we think about variance, we're thinking about how does the data affect how well our hypothesis can fit the data set. If we think about a hypothesis with high variance, then what does it look like? The hypothesis tends to be very complex. It has a lot of degrees of freedom because it's complex, right? It has a lot of parameters that we can fit. So it tends to be quite flexible because of the high degrees of freedom. Now, because there's a lot of degrees of freedom, so whenever the training data changes, the learned hypothesis changes a lot, right? Because the function is so flexible, so as soon as the data changes a little bit, the function is able to adapt to that change immediately, so the function also changes a lot. So the result of that is that a hypothesis with high variance tends to fit the training data very well. You might think this is a good thing, right? We have this training data and we want something to fit it well. But remember that our goal is generalization. We want to fit unseen data well. So one problem with a hypothesis with high variance is that we may be fitting the training data too well. We may be reading too much into the information provided by the training data. So we might come up with a hypothesis that fits the training data too well and does not fit unseen data well. This problem is also called overfitting. Now back to this graph a little bit. You can see that on the left-hand side, we have a model that with high bias, hypothesis with high bias. So this model is generating high error and does not fit the data well because it's too simple. It makes too strong of assumptions, so it doesn't fit the training data well. Therefore, we can't hope that it even fits the unseen data well. On the other hand, on the right, we have a hypothesis with high variance. And this hypothesis is too complex, too flexible. So it may fit the training data well, but it may be doing that too well. So it may be overfitting to the training data, and therefore it does not fit the unseen data well. This is 2 points where the model is having a high error and we want to find some point in between. This is another nice set of pictures to illustrate the bias and variance trade-off. First of all, we have a function, a hypothesis with high bias. It's really simple. It's just a straight line. It makes very strong assumptions. It's not flexible at all, right? You can see that if the data set changes a little bit, it probably doesn't change very much because it makes this very strong assumption. And also, you can clearly tell it does not fit the training data well. On the other hand, we have a model, a hypothesis with high variance. This hypothesis is really, really flexible, right? It's able to adapt to each and every individual data point. So it goes through every data point, but you can imagine if the training data changes a little bit, some data points move around a little bit, then this function is going to drastically change, right? And we want to find some point in the middle where we have both low bias and low variance. So low bias means we're not making a very, very strong assumption on what the function looks like. We have some degrees of freedom, right? It's not so rigid like a straight line. But on the other hand, we are also not adapting too much to the data set, right? We don't have too much freedom to adapt to whatever data point that we have. We have some freedom. So this is a sweet spot in the middle that we want to get to. How do we find a hypothesis that has both low bias and low variance? Well, one technique is to use cross-validation. The main idea of cross-validation is that typically we do not have access to the unseen data until our hypothesis is ready. Unseen data is also called a test data. Because we don't have access to test data, what can we do? Well, we only have access to our training set. So let's split up our training set, use part of it for training, and then use the rest of it as sort of an example of test data. Basically, that's all we have. So let's use part of our training data to mimic what test data look like so that we can use it to evaluate different hypotheses and choose the best one. The picture on the slide illustrates how we do four-fold cross-validation. I've also explained the general process on the next two slides, but let me talk about the idea using this picture. So to do cross-validation, we first decide on the number of folds. This is usually called K. Here, K is equal to 4. Typically, we will do 5 or 10-fold cross-validation. So once we decide on the value of K, we are going to take our training data. So here, the entire box represents all of our training data. We'll break the training data into 4 equally sized partitions. Right here, what's happening is that I have broken up the training data into 4 partitions like so. And then for each fold, see, for four fold, we're going to do the training 4 times, right? So for each fold, we will leave one partition as the mimicking the test set. And we'll call this set the validation set, validation data. And we'll use the rest of the partitions, here the 3 other partitions, as our training set. So we'll train on our training set and then test on our validation set. So using this last partition to get the accuracy of our hypothesis. We will do this K times. So 4 times. Each time we will choose a different partition as our test set or our validation set, like so. Once we've done this 4 times, we will get 4 different values, right? For each fold, we will get one value, which is our which is our test accuracy or test error, right? Because we learn a hypothesis on the 3 partitions, and then we'll test on the validation set and get 1 error. So we'll get 4 different errors, and we will take the average of these errors. That will be a performance measure for this particular hypothesis that we're looking at. So overall, our hypothesis may have a set of parameters, and we need to choose values for these parameters, right? So for each set of parameter values, that's one possible hypothesis. We will take each possible hypothesis, do this cross-validation, get one average prediction accuracy or average error, and then we'll use this value to compare different hypotheses, and we'll choose the hypothesis with the best, with the smallest average error or largest average prediction accuracy. So after cross-validation, what do we do? Well, what cross-validation gives us is a set of parameter values that's best, right? That represents the best hypothesis we have found. So we can do one of 2 things. When we were training this hypothesis, we already got a few different trained hypotheses. We can just choose one of them as our final hypothesis. Or we can go back and take all of our training data. Since now we can use all of it, why not? So we can take all of our training data, use the parameter values we got from cross-validation to train a new hypothesis. Either way, cross-validation tells us which hypothesis is the best, and then we just do some training to get the actual hypothesis for testing later. Finally, Let me conclude this video by talking about overfitting. Overfitting is closely related to the bias and variance trade-off, but I will talk about this in the context of cross-validation. So when we do cross-validation, we split up our training data into training set and validation set. So as our model becomes more and more complex, how does our expected error on these two sets change? This picture illustrates that very well. So as our model becomes more and more complex, our training error will always decrease. So we can always make our training error smaller by making the model more and more complex. But do we want to do this? Turns out we don't, because our error on the validation set really tells us what we want to do. If our model is too simple, we run into a problem of underfitting. So underfitting means the model just does not have enough degrees of freedom to capture all the useful characteristics in both the training set and the validation set. So it doesn't fit the training data well. It also does not fit the validation set well and has large error. On the other hand, if the model is too complex, we run into the problem of overfitting. So here, what's happening is that the model is paying too much attention to the training data. So it's not only capturing the common characteristics between the training and the validation data, it's also capturing some characteristics that's only present in the training data and it's not in the validation data at all. Because of this, we are doing really well on the training data, right? We have low error on the training data, but we have relatively high error on the validation data. So what we want to find is somewhere in the middle where the model complexity is reasonably complex. So it has enough complexity to capture the common characteristics between the two sets, but it doesn't have too much complexity to be overfitting to the training data. Let me summarize. After watching this video, you should be able to do the following. Explain the bias and variance trade-off. What is the bias of a hypothesis? What is the variance of a hypothesis? Give some examples of a hypothesis that has high bias, high variance, and low bias and low variance. Describe how we can use cross-validation to find a hypothesis with low bias and low variance. Describe overfitting. That's it for this video. I will see you in the next one. Bye for now.